Hello everyone, welcome to the robotics module. Today we are going to look at the first part of trajectory planning. Here is the outline. First, we will have a recap on what we studied last time. Next, we will have an introduction to trajectory planning. We will mainly look at trajectory planning in joint space, and we will do that using third order and fifth order polynomials. And finally, we will look into the problems associated with polynomial trajectory planning. Last time we mainly looked at the manipulator singularities. So the configurations where the rank of the Jacobian matrix is less than its maximum value were called singular configurations. And the rank of the J matrix is not a constant and it depends on the configuration at that moment. We can determine manipulator singularities using the Jacobian matrix, that is, when the determinant of J equals 0, there we have a manipulator singularity. For a 6 degree of freedom manipulator that has a spherical wrist, we can decouple arm singularities and wrist singularities. Wrist singularities occur when determinant of J22 equals 0, whereas arm singularities occur when the determinant of J11 equals 0. Today we are going to look at how we can plan a trajectory for a robotic manipulator. We use robotic manipulators to perform various tasks at high speeds, high accuracy, and with hefty payloads that are difficult to be achieved by regular human capabilities. It can be an assembly line where you need to pick and place objects, or it can be an automotive manufacturing plant where vehicles are assembled, or else it can even be on space shuttles where you need to carefully handle payloads. As you can see here in this video, whatever the scenario is, we need the end effector of the robot manipulator to follow a certain path. First, we need to understand the difference between a path and a trajectory. A path is a spatial construct that connects two points or two poses A and B. So we will have, let's say, A here and B there, and we can connect these 2 points by something like this. Okay, so this is a path. Then what is a trajectory? Simply put, trajectory is also a path, but it has timing information. So if you take the same path as before, so something like this, now we are going to insert timing information to this path. So here, let's say the time is t equals 0, and at this point, let's say it is 10, and here we have 15, and maybe finally we have t equals 25. Okay, so this is a trajectory. When we plan a trajectory for a robotic manipulator, we can do that in two ways: joint space trajectory planning and workspace trajectory planning. Which method to choose depends on your requirement. Now let's say the initial configuration of the manipulator is something like this. So we have our base link, and here we have another joint. So let this be Q1, the joint variable, and this is Q2, and here we have the end effector XY. Okay, and the final configuration is So here we have the final Q2 and here we have Q1. Okay. So in joint space trajectory planning, we plan the manipulator motion considering how the joint variables are changed. And when we do that, the motion in the workspace would be unpredictable. So in this case, Q1 is going to change from 0 to, let's say that final angle is 135 degrees. So here this is 0 and this is our final angle. Okay. And for Q2, the initial angle, let's say it's 90 degrees and final angle is 30 degrees. So that is, here Q2 is 90 at the beginning and here it's 30, right? Now in workspace trajectory planning, we plan the manipulator motion considering how the manipulator end effector as well as all the rigid links are changed in Cartesian space, right? So in this case, we should be careful because we may pass through singularities in between. So here, our initial configuration corresponds to the Cartesian force of, let's say, 2, 1. So here I'm talking about this point. Okay, so that end effector position changes from 2, 1 to, let's say, the final force is -3 and 1.2. Okay, so that is this final point. Okay, so here we are talking about change in the end effector position in Cartesian space. Okay, let's say we want to achieve straight line motion of the end effector, as we can see here in the left figure. So definitely we have to trajectory plan in the workspace, right? Nevertheless, due to the geometry of the manipulator, we may require sudden change in joint angles when we traverse through the given line, right? That is, if we look at the figure on the right, you can see up to, let's say, this point along the line, the manipulator would take a right hand approach, but because of certain joint constraint we might have for this particular joint, the manipulator needs to approach the next point from a left hand configuration, right? And thus the manipulator has to change joint variables very rapidly. Understood? Let's look at the steps to be taken when we plan trajectories in workspace. Again, let's say we want the end effector to follow the straight line from A to B. Okay, so our first step is going to be to calculate the path from A to B in Cartesian coordinates. Okay, and after that we will assign a total time t for the traversal because we are dealing with trajectories, so the path should contain time information. Next, we will discretize the points in time and space. So that means after this discretization, each point will have a coordinate and a timestamp. Next, we will create a continuous time function between these points. And finally, we will solve inverse kinematics at each step. So what are the advantages of trajectory planning in workspace? Now, since we are dealing in the Cartesian coordinate system, and since we know where the obstacles are in the workspace, we can plan a collision-free path in the workspace. Okay? And what are the disadvantages that we have in planning in workspace? Now, as you can see, we have to do non-stop calculation of inverse kinematics, and that can be computationally intense. Okay. When we plan trajectories in joint space, we mainly look at the initial configuration and the final configuration of the manipulator. That is, we really do not care about the intermediate motion of the manipulator. Okay? For example, in a pick and place task, we should know where the materials are and where they should be placed. It can take whatever workspace trajectory in between, as long as there are no obstacles to collide with, right? So the steps to be taken in joint space trajectory planning are as follows. First, we calculate the inverse kinematics for the initial and the end poses only. Next, we assign a total time t using maximum velocities of the joints. Next, we discretize the individual joint trajectories in time. And finally, we will blend a continuous time function between these points. Okay, so what are the advantages of joint space trajectory planning? Now we have to compute inverse kinematics only once, right? And also we can take into account the constraints that we have in joint angles and joint velocities. Now the disadvantage of joint space trajectory planning is we cannot deal with workspace obstacles because everything is handled in joint space. Okay. In this module, we are only going to look at trajectory planning in joint space. A given robotic manipulator will have n number of joints. Let's consider trajectory planning for a single joint first. And afterwards, we can extend the concept to all other remaining joints exactly the same way. Okay? So let's suppose at t equals t0, the joint variable satisfies these conditions. That is, at the beginning, we have joint position as q naught, velocity as v naught, acceleration as alpha naught. So we have the initial conditions at t naught like this, okay, and at t equals tf, the joint position is qf, joint velocity is vf, and joint acceleration is alpha f. So here we have tf, and this is the single joint that we are considering, and this is our motion. Okay, and these are our constraints. Understood? Our first candidate to create a trajectory between two given poses is to use polynomials. The joint trajectory that we are going to generate between two configurations should be a smooth trajectory. That is, its first few temporal derivatives, the velocity, acceleration, and jerk, which is the derivative of acceleration, should be continuous. Okay, so this is the derivative of acceleration. Now polynomials are simple to compute and they provide required smoothness, and it is easy to assign the boundary conditions. Now if we have 4 constraints to satisfy, then we need polynomial of 4 independent coefficients. That is, we can use a third order or a cubic polynomial for this purpose. So we can write this as qt, which is the joint trajectory, is equal to a0 plus a1t plus a2t squared and a3 tq. Okay, and its first temporal derivative, which is velocity, q dot t is equal to a1 plus 2a2 t plus 3a3 t square. Okay, so at t equals t naught, we can write the above equations using the constraints. So at t naught, the joint position was q naught, therefore q naught is equal to a naught plus a1 t naught plus a2 t naught squared plus a3 t naught cube, and the joint velocity was v naught, so we can write that as a1 plus 2 a2 t naught plus 3 a3 t naught square. Okay, and similarly when t equals tf, we can again write the remaining two constraints, that is joint position is qf is equal to a naught plus a1 tf plus a2 tf squared plus a3 tf cube, and so we have the velocity vf equal to a1 plus 2 tf plus 3a3 tf square. Okay, now we can put this into matrix form. So our constraints vector is q naught, v naught, qf and vf. Okay, so that is equal to, the coefficient vector is a0, a1, a2 and a3, which is what we need to figure out, and the matrix is going to be 1 t0 0 square t0 cube. In the second row we have 0 1 2 t0 and 3 t0 squared, and for the third row we would have 1 tf squared tf cube, and finally we have 0 1 2 tf and 3 tf squared. Okay, so I will call this vector as B and this matrix M and the coefficient vector as A, and if we find the determinant of M, you will find that to be tf minus t0 to the power of 4. Okay, and when tf is not equal to t0, that is when the time interval is non-zero, the above equation will always have a unique solution, and that is given by M inverse times B. Okay, let's do an example for cubic polynomials. Let's say we have t0 equals 0 and tf equals 1. v0, that is the starting velocity, is 0 and the end velocity is also 0. So that means the manipulator would accelerate and finally it would come to a halt, right? So with these values we would have the M matrix to be 1 0 1 0 0 1 1 1 and 0 0 1 2 and 0 0 1 3. Next we have A0, A1, A2 and A3, the coefficients that we need to figure out, and this is equal to Q naught, that is the starting joint angle, then we have 0 and QF and 0. Alright, now in this case there is no need to find the inverse of the M matrix, and it is straightforward to find all these coefficients. So we see that A naught is equal to Q naught, right? And next we have A1 is equal to 0, right? And from the third row we can write A0 plus A1 plus A2 plus A3 equals QF, and A naught is Q naught and A1 is 0, right? So we have A2 plus A3 equals QF. Maybe we can send Q naught to the other side. So we have one equation from that, and also we can again write the equation from the fourth row. So A naught times 0 is 0, so we don't need this one. Then we have A1 plus 2 A2 plus 3 A3 equals 0, right? So A1 is also 0, therefore we have 2A2 plus 3A3 equals 0. So we have two equations, and we can solve for A2 and A3. If we do that, we find A2 equals 3 times QF minus Q naught, and A3 equals minus 2 times QF minus Q naught. Okay, so we have found the coefficient vector, and therefore QT, the trajectory function, is A0 plus A1t plus A2t squared plus A3t cube, the cubic polynomial, and from that we find Q0 plus 3 times QF minus Q0 t squared minus 2 times QF minus Q0 t cube. So here we have found a cubic polynomial that satisfies the given constraints. Okay. Say for example we have Q0 equals 10 degrees and qf equals minus 20 degrees, then if we plot the joint trajectory, joint velocity and joint acceleration, we would get these smooth curves. Okay. If we look at these three curves, the joint trajectory and the joint velocity has smooth curves. But in the joint acceleration, you can see there is a discontinuity at t equals 0. The derivative of acceleration is called jerk, and what we have here is an impulsive jerk. The problem with that is it induces vibration in the manipulator. So how can we overcome that problem? Now we can enforce two more constraints, that is acceleration constraints, right? So altogether we can have 6 constraints instead of 4, and we can have a fifth order polynomial to ensure that we have a smooth curve for joint acceleration as well. Okay. A fifth order polynomial is also known as a quintic polynomial. So shall we write equations for joint trajectory, joint velocity and joint acceleration using quintic polynomials? So we can start with qt, the joint trajectory, which is equal to a naught plus a1t plus a2t squared plus a3t cubed plus a4 t to the power of 4, and finally a5 t to the power of 5. So here we have a fifth order polynomial for the joint trajectory. Now I take the time derivative of this to obtain q dot, and that should be equal to a1 plus 2a2 t plus 3a3 t squared plus 4a4 t cubed, and finally 5a5 t to the power of 4. Okay. Since we are also considering the acceleration constraints, we take the time derivative of the velocity, and we have the joint acceleration qt double dot, and that would be equal to 2a2 plus 6a3t plus 12a4t squared plus 20a5 t cube. Okay. Now for the constraints, we can consider the two configurations. First, for t equals t naught, we can substitute for t, so all these would become t0, t0, and initially our joint angle, let's take that as q naught, and the initial joint velocity can be v naught, and the initial joint acceleration, we can take that as alpha naught. Okay, so here we have one set of equations, and for the second configuration, that is when t equals tf, we can replace t with tf, so the final joint angle, let's take that as qf, final joint velocity is vf, and the final joint acceleration can be taken as alpha f. Okay. Again, we can put this into matrix form. So for the first row, we would have 1 t0, t0 squared, and t0 cube, t0 to the power of 4, and finally t0 to the power of 5. And for the second row, we would have 0, 1, 2 t0, 3 t0 squared, and 4 t0 cube, and finally 5 t0 4. For the third row we have 0, 0, 2 and 6 t0, 12 t0 squared, and 20 t0 cube. And similarly for the fourth row we have 1 tf, tf squared, tf cube, tf to the power of 4, and tf to the power of 5. And fifth row we have 0, 1, 2 tf, 3 tf squared, 4 tf cube, and 5 tf to the power of 4. And for the final row we have 0, 0, 2, 6 tf, 12 tf cube, that is 12 tf squared, and 20 tf cube. Okay, so we can find the coefficients of the quintic polynomial by taking the inverse of the M matrix and multiply that with the joint constraints that we had, the joint angles, joint velocities, and the joint accelerations. Understood? If we look at the graphs for joint angle, joint velocity, and joint acceleration, here we see we have smooth curves for all three variables, right? And on the left hand side we have zero velocity boundary conditions, that is we start with zero velocity and end at zero velocity. And on the right hand side what we have is 0.5 initial velocity. Okay, now I want you to identify two main problems associated with polynomials. You may pause the video now and can you try to find them? So assuming that you took some effort to recognize the problems, the first problem we have is when we have non-zero initial velocity like this. So if you look at this plot where we have the joint angle change, so we start with zero angle and we move towards joint angle 1. But in between you can see actually the joint angle has moved past 1 and has come back. So we have an overshoot, right? So from 0 to 1 it has gone to 5 in between. Alright, so for non-zero initial velocity we see the polynomial overshoots. Okay, so that is one problem we have with the polynomials. Were you able to find another problem associated with polynomial trajectory planning? Now if you look at this curve where we have the joint velocity, you can see that most of the time the velocity is far less than its maximum velocity. Now we use manipulators in industries to make things fast, right? So we want the manipulator joints to operate at least close to their maximum velocities. So it is not happening here, right? So this is a problem that we have when we use polynomials. That is, the mean velocity is too less than the maximum velocity, right? So this is our second problem. Okay, now we saw the problems associated with polynomials, and we would use other techniques to overcome these problems. Okay. With that, we have come to the end of the first part of trajectory planning lecture. So manipulated trajectory planning can be performed in either workspace or joint space. We mainly looked at joint space trajectory planning. One technique is to use polynomials for joint trajectory planning, and if we have 4 constraints, then we can go for a third order polynomial. And if we include the acceleration constraints, so altogether we would have 6 constraints, and therefore we can go for a fifth order or a quintic polynomial. We finally recognized 2 main problems associated with polynomial trajectory planning. So there is an overshoot problem if there is non-zero initial velocity, and also we saw that the mean velocity is far less than the maximum velocity of the joint. Thank you very much.